Determine the force in members FD and BD of the frame. So we take a look at our frame and we locate our members. This one member, this is the other member. Also find the horizontal and vertical components of the reaction. The pin at C exerts on members ABC and EDC. So find the pin at C. Right there is C, that's the pin at C. And it connects this member ABC right here and member EDC right there, as well as the wheel. And it's rare that a pin connects 3 members, but when it does, you got to go slow and it's a lot more tedious. Well, this pin at D is also connecting 3 members, but they're a very special member F to D and a very special member B to D. What's special about those 2 members? They're 2-force pin connected members, so I don't have a whole lot. It's just either tension or compression, so that's a lot simpler. But is the member ABC a 2-force member connected at pin C? No. Neither is EDC a 2-force member pin connected at C? No. So it's a little more complex. So these are the things we want to solve for. The force in that member, the force in that member, and for member ABC, that member's reaction, CX and CY, that's the horizontal, that's the X, and the vertical, Y, component of the reaction, the pin exerts on that member ABC. All right, so these are the 6 answers that we want to solve for. How do we approach a big problem like this? Well, we read the problem over about 2 or 3 times, try and understand what they're asking for, try to get some good symbols for what they're asking for, play with our illustration a little bit, but then when you have a large frame with multi-members, if you can, do a free body diagram of the entire frame and look to determine the supports, the reactions at the supports. So if I did a free body diagram of the entire frame, I would have the normal at A. I know we didn't ask to solve for normal A, but I anticipate I'm going to need it, as well as the normal at C. Now, this frame includes all of member GFE, all of member F to D, all of member ED, C, all of member. You're kind of saying, isn't that obvious? But now I'm getting to the point I really want to get to. It also includes the entire wheel at A and the entire wheel at C. That's part of my frame. So when I'm cutting the free body diagram, I'm cutting right underneath the wheel at A and then the supporting ground. And so that's what's happening there. Likewise, I'm cutting right underneath the wheel at C, and then I free my object and then draw that free body diagram of that frame. So we can solve for the normal at A and the normal at C. I think some of the moments, let's say about this contact point right there, or at pin C, or at pin D, or at pin E, any of them, because they'll take out n sub C out of the equation. There won't be a moment that n sub C generates about any of those points, because n sub C's line of action goes through all of those points. When we do that, we did determine that n sub A times 1 plus 2 plus 1, which is 4 meters, is equal to our 12 kilonewton. Whoops, can't write today. N sub A times our 4 meters is equal to, that makes it want to rotate in the clockwise, 12 kilonewton times its moment arm of just 2 plus 1, 3 meter. And you solve for N sub A, and it comes in at, what is that, 36 divided by 4? What is that, 9 kilonewton. And then we solve for N sub C, do the sum of the forces in the Y. So 12 down plus 9 up, we still need 3 up, 3 kilonewtons up. So we solve for N sub A and N sub C. All right. Now, to get in here and to solve for the force in this member and the force of that member, we need to get some individual free body diagrams. So there's a lot of choices. You could get a free body diagram of the horizontal member GFE. I encourage you to do that. We're going to need that. Get a free body diagram of, you could even do this one, just FD. It's just that member, FD, by itself. It's either in compression or tension. We look at it, you look at it, and I suspect it's going to be in compression. All right. Get a free body diagram for member B to D. Likewise, that's going to be in compression, just inspection, looking at it. The member EDC, the member ABC, all of these we can get free body diagrams. There's a lot of free body diagrams we can get for this problem, as well as we can get a free body diagram of just the pin at A, as well as the wheel at A, and the pin at C, as well as the wheel at C. And for this problem, I know that it will take you a long time to solve this problem, you know, the first time in a problem like this, but I really encourage you to do it. I don't have a lot of time to do it, but I encourage you to do it. Get a free body diagram of every one of those things. Okay, let's take a look at probably the easiest one would be this horizontal member. So I'm just going to sketch that horizontal member at G, and then we have F, and then we have E. And what do we have? We have our load of 12 kilonewton. We're going to have this member is going to be in compression. So it'll be a force acting at point EF, and it'll have that force in F to D, and then it'll have some unknown reaction at the support. We look at it, we suspect that it's going to be E positive X in that direction, and E positive Y in that direction. Okay, what can we do with that free body diagram to solve for one of our unknowns? And the one unknown that we can now solve for is this force in member FD. We can solve for that, can't we? How would we do that? Using this free body diagram? Some of the forces in the Y, but we have this EY is unknown still. Sum of the moment is usually our go-to equation. Let's do the sum of the moments around a particular point. Because this is unknown, and this is unknown, do the sum of the moments around point E to take two of the unknowns out. You know, I'll get one equation, one unknown, right? So we need to use also our similar triangles. We're getting really good at those similar triangles, but they help us pick off components of a force that's not aligned with an axis. This one is a 1, 2, square root of 5 similar triangle. If you have any questions about that, just see me during office hours. Maybe we need to refresh. Maybe if you're still struggling with similar triangles, we need to get over that hump. Okay. Okay, so if we do the sum for this free body diagram, if we do the sum of the moments about point E, that has to equal 0, our equation is we're going to have 12 kilonewton, and then that moment arm distance is going to be 2 meters. Sorry, I just scrolled down from our illustration. And then we're going to have making it want to rotate in the opposite direction. Oh, it's 3. You're right, it is 3. I scrolled down and then I couldn't read it very well. It's 3 meters. And then we're going to pick off the component, which is our 2 divided by the square root of 5 times the force F to D. And that moment arm distance is 1 meter. One equation, one unknown. Can people verify that this is the answer right here for that? 40.25, yes. A couple more verifications, thank you. Thank you, thank you, thank you, thank you. So we're able to solve for that 40.25. The force, remember, F to D is 40.25 kilonewton. All right. Now, I suspect I may need E sub X and E sub Y later. Why not solve for them? They're not asked for, but I suspect I'm probably going to need them later. Okay, If we solve for E sub x, you would do the sum of the forces in the x for that member must equal to 0. And what we're left with is we're left with the 1 over the square root of 5 times the force F to D, which we just calculated, is equal to E sub x. And then we solve for E sub x. No, I probably didn't solve for it. No, it's 18 kilonewton. And then we could solve for E sub y. And E sub y is some of the forces in the y, and it comes in at 24 kilonewton. You agree? No, good? Anybody else agree on those two? All right. So we're diving into this problem. We've already solved for one of the unknowns. Okay, now we can come down here and we can do the same thing for this horizontal member ABC. Okay? But before I get to that, I really want to talk a little bit about that wheel at A, so that then I can talk about the wheel at C. All right. So let me see if I have this. Okay. If I focus on the wheel, if I just have the wheel at A, it's hollow in the middle because the pin could be included as part of the wheel or it could be excluded as part of the wheel. I'm going to leave the pin out. The pin at A is not part of the wheel. It's something that slides in the middle of the wheel at A. And so there's my pin at A. This is my wheel at A. This is my pin at A. All right. And then later I'm going to need my member ABC. And it has a hole in that in which the pin slides as well. Okay. So let's do this. We have the normal at A acting on the bottom of the wheel, and we solved for that, and we calculated that normal at A to be, what is that? I forgot. How much was it? 9 kilonewton. Is there anything on the top of the wheel acting? No. The only thing is I have a pin riding in the middle of the wheel. And guess what the pin's going to do? It's really going to be resting on the bottom of the hole in the wheel. It's going to be resting down here. And so it's going to be exerting a downward force right there, kind of on the bottom part of that hole in the wheel. That'll be some, let's say the force, how do I describe that? Let's say the pin, I'm going to say the AY due to that pin. I'll just leave it AY of the pin. So then if we focus on the free body diagram of the pin, guess what? We're going to have something acting on the bottom of the pin, because this isn't the bottom of the pin resting in the bottom of the hole in the wheel. And that's going to be my AY upward. Well, but I also have the top of the member ABC pushing down on the top of the pin. So I have another equal and opposite AY due to the member ABC. So maybe we put this AY of the wheel, and then we put AY of ABC, and then over here we're going to have, acting upward, AY on member ABC. What's that due to? The pin that's sitting in the hole of the wheel, etc. So we have the free body diagram of the wheel at A, the pin at A, and then that member ABC. I've just focused right there at that location A for a second. Do you see how these are equal and opposite? They tie together. Now you're saying this is kind of belaboring a point, isn't it? Because if this is 9 kilonewtons, guess what that is? 9 kilonewtons. So this is 9 kilonewtons. That's the same thing. That has to be 9 kilonewtons, and that has to be 9 kilonewtons. I know. You're right. A lot of times we go so fast we just kind of skip all that. We just say, oh, here's 9 kilonewtons applied to the member ABC at that pinned location. Force upward. Okay. And then we come over here, and at location B, we're going to have a force that comes like this. That'll be the force in member B to D. And then this is where I needed to spend a little more time. I have a hole in my member ABC. There's a pin in that hole. And that pin exerts a force. Now I can look at it for a minute, and what do I think that member needs a force in the positive direction for the, let's call it the C, because it's a location C, Y on member ABC? It probably is going to be positive, isn't it? And then because this force, this member right here, B to D, is in compression, it's probably going to need to have a force in that direction for some of the equilibrium and some of the forces in the X equal to 0. So C, Y, A, B, C. It's like I have a hole in my member ABC, and I have some force that the pin exerts in the X as well as in the Y at that hole. All right, now that I have this and it worked out, how can I do the equilibrium for this member ABC? Let's do the sum of the moments about point C equal to 0. If we do the sum of the moments about point C, this similar triangle is a 1, 1, square root of 2. So right here I have it in the illustration. So what we get is we get that, I'm going to just put the AY, ABC times the moment arm distance. What is that moment arm distance? Isn't that 4 meters? Is equal to the force B to D. And I pick off the 1 over the square root of 2 component, the downward directed component, and its moment arm distance is 1 meter. Okay, so we get the force in member B to C. It will be that 9 times 4 times the square root of 2, and it comes right in at 50.91 kilonewton. Okay, B to D, B to D, B to D. It'd just be easier if I put this all in PowerPoint and just click through it and I read it. Would that be better? The problem is it keeps you on your toes because you know I make mistakes when it's not PowerPoint. Okay, so now we can do the sum of the forces in the X equal to 0 for the same member, ABC. And we get that 1 over the square root of 2 times FBD, which we just solved for, is equal to, why did I write CY right there? Shouldn't I have written CX? Sorry about that. CX in the ABC. And then we solve for CX on member ABC, and that comes in at 36 kilonewton. And then we do the sum of the forces in the Y on that member must be equal to 0. We get an equilibrium equation. We get our, I'm just going to write it 9 kilonewtons upward plus CY on ABC upward equal to 1 over the square root of 2 times that downward 50.91 kilonewton. Hence CY ABC is equal to 27 kilonewtons. So now we were able to really focus on this member ABC and solve for 3 more of the unknowns. Okay, let's review again. This is sort of long subscript notation. What does it mean to have CY, comma, ABC? Yes. That's exactly it. The subscript ABC means I'm focusing on this member ABC. And it has some location C, when we're thinking about a hole at C. And there's a pin that's in that hole, and it's exerting a force on that member ABC. And in this case, it's positive 27 kilonewtons upward. Likewise, the same description of this 36 kilonewton. Yeah. So it's acting on the member ABC. All right. Well, we only have a little bit to solve for. We have to focus on what is the force that the pin exerts on member EDC. And this is where I want to spend a little time talking about the wheel at C, the pin that goes through the wheel at C, and then both of those members. We just already talked about how the member ABC is connected to that pin, but then also the other one. So in the interest of time, that's already talked about. I tried to blow this up and help you a little bit. And so really, we already just talked about this, didn't we? And we just talked about this member. Okay. And so really what I want to do is focus on the discussion down here. So if I start and I try to isolate the free body diagram of the wheel at C. The wheel at C, I know I don't do a very good job, but it's got a hole in it. And I'm not trying to show the pin there. It's just an empty hole. And the pin right here is a separate free body diagram for the pin. Okay. So on that wheel, I have an upward force, N sub C, on the bottom of the wheel. And we already solved for that. N sub C was 3 kilonewtons, wasn't it? And then we have that pin. And that pin in the middle of the wheel exerts a downward force on the wheel. That's CY subscript wheel, downward. And I can already solve for that one. That's 3 kilonewton due to the sum of the forces in the Y have to equal to 0 for the wheel. All right. But then I focus on my pin. And this is probably the most challenging part. Is for the pin, I have a wheel pushing upward on that pin, and we already calculated that's 3 kilonewton. Okay. We also have a member ABC. This member ABC, we had a CY with the pin exerted on the member, and we just calculated that to be a positive. Let me try and draw it over here. What was CYABC? It was 27 kilonewtons, wasn't it? So this was 27 kilonewtons downward on the pin. Because if the pin is pushing up on the member ABC, then member ABC is pushing down on the pin with the same magnitude, 27 kilonewton. Okay, we can just focus on the Y member. But also the member ECD is connected, touches the pin, interacts with the pin. And in this case, you do a little thought process, and if that pin gave way, this whole member would probably lift up, and the whole thing would probably try to pivot around here or around this point, and would try to fall that way, wouldn't it, if that pin broke? And we talked a little bit where that pin needs to hold this member EDC down. And so if it's trying to hold this member EDC down, then the pin feels an upward force equal and opposite from the member. So focus on these two things. They're consistent, aren't they? They're both. One is on a free body diagram of the pin, one is on a free body diagram of member EDC. So we agree that, okay, the pin is holding this member down, hence the pin feels an upward force due to that member. At this point, now I can do the sum of the forces in the Y equal to 0 for the pin at C, and I can solve, and so we have, this has to be 24 kilonewtons up. Does that make sense? Yeah. Okay. The other was This CX ABC, we solved for that. That's 36 kilonewton. So if the pin is pulling this member ABC to the right, then the pin feels a force to the left equal and opposite of 36 kilonewton, isn't it? All right. That pin is sitting there, and I know it's connected to the wheel, but the wheel doesn't exert anything but in the Y direction. It doesn't exert anything in the X direction. So at this point, I can do sum of the forces in the X on that pin, and guess what CX EBC is? 36 kilonewtons. And I know that if this is pushing it to the left, this has to be to the right. All right. So then I come over here, and this is 36 kilonewton back. Okay. So we solved for, we're focusing on this member EDC. We solved already for the force in the member D to B. That was about 50.91 kilonewton. The force in F to D, that was 40.25 kilonewton. Right? And actually, we just finished out the problem, didn't we? I already saw, these were the last two unknowns. The last two unknown was this one and this one. We really don't, we can analyze member EDC, and it will just show us that our equations are true. It's an equilibrium. I can do the sum of the moments about any point. I can do the sum of the forces in X, sum of the forces in the Y. It'll confirm that the solution's good. Okay. Most of us probably would have avoided focusing too much on the wheel and pin and gone to this member EDC and then solved for the last two unknowns, which were down here and here. Let me pause. Did we solve the problem to your satisfaction? Looks good?